This is an atom, the fundamental building blocks of the universe, making up everything from you to the screen you're watching this on, to my cardboard cutout of Danny DeVito. And this is Scratch, a children's programming language that runs in your web browser. But what if, hear me out, we simulated atoms inside of Scratch? To begin, we need to identify what makes an atom do atom things. Like, what is an atom? Why is an atom? And how is an atom? An atom is fundamentally made up of three parts. Their electrons, their protons, and their neutrons. Electrons are negatively charged and orbit around the nucleus, which is made up of the positively charged protons and the neutrally charged neutrons. But how is an atom? More specifically, how do they bond? Atoms bond in three ways. Ionic, which is when an atom gives an electron to another atom. Covalent, this is when an atom shares an electron with another. We also have metallic bonding, which is when a bunch of metal ions have electrons swimming between them. And then we have hydrogen bonding, and no one cares about hydrogen bonding, so we just pretend like they don't exist. So with the fundamentals laid out, let us begin. In my first attempt, I utilised clones to act as the atoms, but using clones has some caveats. First of all, clones are very laggy. Second of all, clones in Scratch can't actually communicate private data between themselves without some trickery. Now, this is important as if I want atoms to be able to bond to one another, they have to be able to gather data from each other, such as the electron count. So after sinking a couple hours into that, I shifted my sights to lists. Now, why are lists going to be better than clones? Well, when you think about it, all I was using the clones for were their positions. So instead, I can make an object represented by an ID, with that ID representing a line in every single list. Now we can have X and Y represented by a list instead of the clones, and this goes for everything. Not only is this more efficient, it also removes the cap put in place by using clones. Now, you may be asking, how then do I display these atoms on the screen? Well, don't worry, I'll get to that. So let's try this again, shall we? To begin my first attempt a second time, the first thing I need to do is get atoms to attract to one another. This is simple. We can use these scripts here, finding the distance, finding the angle between the atoms, and calculating the X and Y forces using them, which is then added to the velocity variables. Warning, the next minute will contain maths. You will survive. This brings us to our first formula, Coulomb's law. Now this is the simplest of the formulas I will be using. But how do we calculate the Q in this formula? Well, Q is just the magnitude of the two charges, calculated using the electrons and protons. And K is approximately 8.99 times 10 to the power of 9, which is 8,990,000,000.
Now that's a lot of damage!
This formula gives us the electrostatic force of attraction or repulsion between the atoms. We also need to calculate the van der Waals force. This force is a little funny to calculate. To calculate this, we can use the net force formula, also known as the Lennard-Jones potential formula. This takes in particle diameter, potential well, and the distance. And to calculate the potential well, we can square root the normal boiling point method. This method uses Boltzmann's constant, which is 1.38 times 10 to the power of minus 23, or 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 This sounds stupid, and it is, but it saves time from making a lookup table with thousands of results, and it actually kind of works well. Now on to the next step, calculating and implementing bonds. To calculate bonds, we first need to check whether the atoms have any valence electron space available. Valence electrons are basically the amount of electrons in the last ring of an atom, visualized here using Bohr's model, with each ring or shell having a different number of max electrons. The first has a max of 2, then we move into our second, which is a max of 8, and the third has a max of 18, or does it? Electrons fill from the lowest energy state to the highest one. The first 8 electrons will go into the third shell, At this point, it's stable. But if we want to add more, the next 2 start filling up the 4th shell. Then the next 10 will go back to that 3rd shell again. Now, although this is how it works in real life, due to simplifying the simulation, we will treat them as if they had a limit of 8, as I'm going to follow the Octet rule, which states that the main group of elements tend to bond in a way that gives them 8 electrons in their valence shell. This is not a perfectly accurate method, but the simulation is never going to be perfect. Unless, of course, you want to simulate the electron field, but I don't want to go into wave functions, please, I beg you. Unless we get 10,000 likes. I think this is also a very important moment to state that this will not be perfect. I'm not a chemical engineer, I'm not a physicist, and I learned this all on my own time. I wanted to go into the quantum level, but I'm using Scratch. But you know who is a chemical engineer? This is Olivia, a friend of mine. And we had a good chat discussing certain aspects of atoms going into the molecular interactions between them. So thanks for your help, just shout out to you, you know who you are. To finish off the bonding maths, we can simply have an integer value that represents the number of electrons connected to said atoms, and use that to limit the connections. We also limit the bonds to triple bonding, as statistically and in reality you aren't going to get quadruple bonds. But fun fact, you can get quadruple bonds in very specific circumstances. For example, it has been seen in comets, and that's what actually gives a comet a fluorescent green glow. Now atom bonds can join, but how do we calculate the strength of those bonds? This is starting to get a bit repetitive, so here's the formula I used. It's a modified Morse equation. This gives us the strength, but I actually need its velocity. Hey, Sick Ravo here. Just wanted to point out that the velocity version of this formula is for more calculating when to draw the visuals of the bonding lines on the screen. Sorry for the interruption. As although this gives strength, I need it mainly for detecting the breaking of bonds. So I use the chain rule to get the velocity version of this graph, which is easy to use in my case. Note, I use both the function and the derivative. Now rendering is quite simple. Since I can already access the atom's X and Y positions and what element they are, I can loop through the positions and stamp the icon representing the atom using the pen functions. So after over 10 gigabytes worth of footage recorded and way too much of my time I will never get back wasted, I give you an atom simulation in Scratch. So here is the final simulation. Now, there are some really cool things, some basic things you can do with this really, but the main thing is being able to create molecules, which is create some O2. There are some pre-made ones, like dihydrogen monoxide over here, which is just water. Now, there are some issues with this simulation, and that's the intermolecular forces aren't quite working correctly when it comes to bonds. And this comes to really down to the scale of the simulation. We are working with Scratch scale here, meaning that we've got a certain amount of pixels by a certain amount of pixels large, and the actual simulation itself have to be scaled to this size. Now, this does cause some very noticeable problems. First of all, if we're scaling to the screen size, we also have to scale the formulas to work correctly at this scale. We run into some issues when scaling up formulas, especially those with exponential functions. You run into a lot of problems because small values suddenly aren't correct. And especially with minute errors, it's very quickly taken out of control. Now, there are some things I've done behind the scenes to help stabilize the simulation. For example, we do have friction. Atoms don't inherently have friction, they don't get slowed down. But on my simulation, basically the velocity is multiplied by a very small number, and this small number just slowly slows down all the atoms over time, and that just helps stabilize the simulation. There's a lot of things like that, and you've got to remember too, these formulas have all been simplified, so there aren't necessarily going to be the most realistic simulation in this case. Another good example of where this comes up is if you make a hydrocarbon. So let me just move the oxygen out of the way. You can hit stabilize to help sort of freeze everything. If I grab a carbon and then grab a hydrogen on that side, grab another hydrogen, and grab another hydrogen, you can really see how it's unstable, and these types of things struggle to stabilize because you've got all the atoms around a single atom, which means all these forces are being applied in every direction of the atom, which makes it very hard for atoms to properly structure themselves. In addition to this is fine like this, a carbon with 4 hydrogens, but as soon as you're getting to larger atoms. For example, if I get a bromine, the bromine is such a big atom, if we get a second atom, although they do attract each other, the actual bromines can't really quite properly connect. And this stability comes from the fact that I'm not properly applying the scale to the distances between the atoms. So you can see here with the fluorine and carbon, there's a larger gap than between the carbon and the bromine. And there's a lot of minor problems like this that have built up over time. Anyway, if you enjoyed this video, it would be nice if you would subscribe, like, especially leave a comment if you would like to, what you would like to see me make next. It takes a long time, a seriously long time to make these videos. This video alone, I spent a month editing. The 3D models you see in this video, all 3D modeled by me. Anyway, until next time, have a good day and don't die.